When Getting Gassed Isn't Ideal, Part 1 is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. These two videos, When Getting Gassed Isn't Ideal, Part 1 and Part 2, are discussions of what to do when PV doesn't equal nRT. Part 1 discusses generalized compressibility, the virial equation, and the Suave-Redlich-Kwong equation. Part 2 does a set of example calculations. The ideal gas equation of state is inaccurate at high pressures and low temperatures. In these cases, the PV-T relationship is more complex. We can categorize the non-ideality of the gas with the compressibility, Z. It is defined as PV hat over RT. For an ideal gas, the compressibility is 1, so the further Z is away from 1, the less ideal the gas's behavior. Z can be greater than or less than 1. To perform calculations for real gases, we often need to know the critical parameters, in particular the critical temperature, Tc, and the critical pressure, Pc. These are defined at the combination of the lowest temperature and lowest pressure at which liquid cannot be distinguished from vapor. When we study phase diagrams, we will explain it further. We should take a look at the range of possible values for the critical compressibility, which is the compressibility calculated at the critical point. You can see from the table that Zc can be as low as 0.23 and as high as 0.31. An informal average gives about 0.27. If we had a chart or table that was designed for Zc equals 0.27, it would be reasonably close for a number of substances. To use such a chart, we're going to need to calculate the reduced pressure, which is the system pressure divided by the critical pressure for the substance of interest. We also need the reduced temperature, which is the absolute system temperature divided by the critical temperature. Here is a figure from data generated by DWSim. In this figure, the critical point is here, circled in red. We're assuming here that all gases have a critical compressibility of about 0.27 and have similar behavior when described in terms of the reduced pressure and temperature. There are a number of similar figures for different ranges of Tc and Pc available in the literature. How do you use these figures? Well, the x-axis is the reduced pressure, and the solid curves are parametric in the reduced temperature. Let's figure out the compressibility at a reduced pressure of 4.5 and a reduced temperature of 1.5. First, we find the reduced pressure of 4.5 on the x-axis. Next, we find the parametric curve for a reduced temperature of 1.5. Then, we sketch a line from the x-axis to the parametric curve. We then go over to the y-axis and read that the compressibility is 0.8. Finally, we multiply the ideal gas molar volume, which we have to calculate, by the compressibility to get the actual molar volume. The generalized compressibility chart is okay for quick calculations, but we probably need something that can be automated or programmed. A number of models have been developed to fit experimental PVT data. Many of them use 3 parameters to fit the data: the critical pressure, Pc, the critical temperature, Tc, and the acentric factor, omega. What is omega? It would take too long to explain how it is measured and why. For now, it is a material parameter available on the web and in other resources. The larger it is, the less symmetric the molecule is. All 3, Pc, Tc, and omega, are determined experimentally. Pc and Tc are usually used to calculate the reduced temperature, Tr, and the reduced pressure, Pr. Many other equations of state, such as Benedict-Webb-Rubin, have additional or different fitting parameters. The virial equation is based on a statistical mechanics or physical chemistry model for molecular interaction, and it's basically a series expansion in the molar volume. The BWR equation is a modified virial equation. For our purposes, we're just going to include the first term of the virial equation, either in terms of V hat or P. The sharp-eyed viewer will note that the B's in the volume form and the pressure form can't have the same value if the compressibility is not 1. We'll ignore that subtlety for the moment. For moderate temperatures and pressures, there are analytical expressions for B, as shown here. Note that they are in terms of reduced and critical temperatures, the critical pressure, and the acentric factor. The truncated virial equation has a less than 2% error for PR is less than 2, and 1 plus B naught PR over TR is greater than 0.8. An alternate way of writing the truncated virial equation is in terms of the compressibility, as you can see here. Again, be sure to check the range of validity for the truncated form if you intend to use it. There is a whole family of cubic-in V-hat equations of state, such as the Peng-Robinson and all of the modifications for the Redlich-Kwong equation. One of these cubic equations is the van der Waals equation. It's important, not because it's accurate, it's not and should never be used, but because van der Waals realized there should be a parameter for the finite volume of the molecules, and a term for the interactions between the molecules. Suave-Redlich-Kwong does it much better. The equation is P equals RT over V hat minus B, minus alpha A over V hat and V hat plus B, where A equals 0.42747 times RTC squared over PC. See, I told you, they use Tc and Pc. B equals 0.08664 times RTC over PC, Alpha equals 1 plus m times 1 minus the square root of tr, the whole thing squared, and m is this quadratic function of the acentric factor. The SRK is a cubic equation in v hat, although you may have to prove that to yourself, so a nonlinear root finder is required if you need to determine v hat. Peng-Robinson is actually a little better for liquids in most cases, but we'll stick with SRK for now. In When Getting Gas is an Ideal, Part 2, we will apply the principles we've learned by working the following example. A stream of propane at a temperature of 423 Kelvin and a pressure of 70 atmospheres is flowing at a rate of 100 kmols per hour. Estimate the volumetric flow rate with ideal gas, the generalized compressibility chart, and the Soave-Redlich-Kwong equation. The measured specific volume of propane at 423 Kelvin and 70 atmospheres is 0.2579 liters per mole. The takeaways from this video are: 1. Real gases are characterized by at least two experimental parameters, PC and TC. 2. When a third parameter is needed for greater accuracy, the acentric factor, omega, is used. 3. Real gas properties can be characterized graphically with the generalized compressibility charts. 4. Real gas properties can also be characterized by equations of state, such as the virial equation and the Soave-Redlich-Kwong equation. Thanks for watching. This video is brought to you by the DOFPro team.